On January 9, 2025, something impossible happened. 3I Atlas, the interstellar comet that has captivated astronomers for months, executed a trajectory adjustment that violates everything we understand about celestial mechanics. Multiple observatories detected the change simultaneously. The object's velocity vector shifted by 0.8 degrees over a 72-hour period. That might sound insignificant, but for an object traveling at over 80 kilometers per second through the vacuum of space, with no planetary bodies nearby to provide gravitational influence, this change represents a physical impossibility. Comets don't just change direction on their own. They follow predictable paths determined by gravity and momentum. Yet, 3I Atlas altered its course, and scientists can't explain why. The detection came from the International Astronomical Union's Minor Planet Center, which coordinates observations of asteroids and comets worldwide. Their automated tracking systems flagged an anomaly in 3I Atlas's predicted position versus its observed position. The discrepancy was small, just a few arcseconds on the sky, but significant enough to trigger alerts. Within hours, observatories in Chile, Hawaii, and South Africa confirmed the deviation. This wasn't a measurement error. This wasn't atmospheric distortion affecting observations. The object had genuinely moved off its predicted trajectory. To understand why this is impossible, you need to understand how objects move through space. Newton's laws of motion govern celestial mechanics with absolute precision. An object in motion remains in motion unless acted upon by an external force. In the vacuum of space, those external forces come from gravity, primarily from stars and planets, or from non-gravitational effects like outgassing in comets. 3I Atlas is approximately 1.5 astronomical units from the Sun right now, well beyond Mars' orbit. At that distance, the Sun's gravity is relatively weak and decreasing as the object moves away. No planets are close enough to perturb its orbit. The trajectory should be smooth and predictable, yet it changed. Before we examine what could cause this impossible maneuver and what it reveals about the true nature of 3I Atlas, make sure you're subscribed and notifications are turned on. We're tracking this object in real time as new data arrives, and you don't want to miss what happens next. Drop a comment with your theory about what's really going on here, because the explanations being proposed are forcing scientists to question fundamental assumptions. Comets can alter their trajectories through outgassing. As they approach the Sun, solar heating causes surface ices to sublimate, turning directly from solid to gas. This outgassing creates jets of material that act like rocket engines, producing thrust that nudges the comet slightly off its gravitational path. This effect, called non-gravitational acceleration, has been observed in hundreds of comets. It's predictable and well-modeled. Astronomers account for it when calculating comet orbits. The James Webb Space Telescope has been monitoring 3I Atlas specifically to detect and measure outgassing activity. And here's where the impossibility deepens. Webb's observations show no significant outgassing at the time the trajectory change occurred. Infrared observations from Webb detect thermal emission from the comet's surface and any gases being released. Between January 6th and January 10th, covering the period when the trajectory changed, Webb took detailed spectroscopic measurements. The data shows faint signatures of water vapor and carbon dioxide, consistent with minimal background outgassing from solar heating. But the detected levels are at least an order of magnitude too weak to produce the observed trajectory change. The thrust required to shift a comet this size, traveling at this velocity by 0.8 degrees in 72 hours, requires significant mass ejection. The amount of gas Webb detected couldn't produce that thrust. Scientists verified this through momentum calculations. They estimated 3I Atlas's mass based on its size and assumed density. They calculated the momentum change required for the observed trajectory adjustment. Then they calculated how much gas would need to be expelled to produce that momentum change using standard rocket equation physics. The answer came out to approximately 10,000 kilograms of material ejected at typical outgassing velocities. But Webb's spectroscopic data indicates maybe 500 kilograms of gas was released during that period. There's a factor of 20 discrepancy between what's needed and what's observed. Researchers proposed several explanations. Perhaps the outgassing is happening on the far side of the comet, the side facing away from Earth and Webb's instruments. Gas ejected in that direction wouldn't be directly visible in our observations. This is possible, but thermal models predict that solar heating should be relatively uniform across the sunlit hemisphere at 3I Atlas's current distance and orientation. There's no obvious reason why one hemisphere would outgas 20 times more vigorously than another. Another possibility involves subsurface reservoirs. Perhaps 3I Atlas has pockets of volatile materials trapped beneath an insulating surface layer. Solar heat slowly penetrates this layer, eventually triggering sudden releases of gas when internal pressure builds up sufficiently. These burst-like events could produce more thrust than steady outgassing while being harder to detect if they're brief. But this mechanism should produce observable changes in brightness as fresh material is exposed, or thermal hotspots as pressurized gas escapes. Neither has been clearly detected. A third explanation invokes exotic ices. Most comets contain water ice, carbon dioxide ice, and smaller amounts of other frozen volatiles. But 3I Atlas formed around a different star, possibly under different conditions. Perhaps it contains unusual ice compositions that sublimate differently than solar system comets. Molecular hydrogen ice, for example, would be nearly invisible to our instruments, but could sublimate vigorously at the right temperatures. Carbon monoxide ice is highly volatile and could produce significant outgassing while leaving faint spectroscopic signatures if present in thin surface layers. Each explanation is plausible, but unsatisfying. They require specific, fine-tuned conditions that seem designed to explain away the observations, rather than arising naturally from first principles. And none of them address another troubling aspect of the trajectory change: the direction. The velocity vector didn't just change magnitude, it changed direction in a specific way. Detailed analysis of the trajectory deviation shows the change isn't random. It's oriented approximately toward the inner solar system, specifically toward a point slightly sunward of 3I Atlas's current position. If this were caused by outgassing, it means gas was preferentially ejected from the side facing away from that direction, which would be the sunlit side. That's exactly opposite of what you'd expect. Comets typically outgas most vigorously from their sunlit hemispheres, and that outgassing pushes them away from the sun. 3I Atlas appears to be accelerating toward a point ahead of it on its trajectory, which requires outgassing from the trailing or night side, where solar heating is minimal. This directional anomaly sparked intense debate. One team proposed that 3I Atlas is rotating in such a way that outgassing jets, even if concentrated on the sunlit side, create a net thrust in the observed direction due to complex geometry and timing. They built computer simulations of tumbling comets with asymmetric outgassing and found specific rotation states that could produce the effect. But their models required very particular rotation parameters that haven't been confirmed observationally. Photometric observations show 3I Atlas varies in brightness with a period around 7.3 hours, suggesting rotation. But extracting the exact rotation axis and angular momentum from those variations is difficult. Another team suggested the trajectory change might not be from outgassing at all, but from radiation pressure asymmetry. Sunlight hitting an object exerts tiny but measurable pressure. For objects with irregular shapes and non-uniform surface properties, this radiation pressure can create small net forces that alter trajectories over time. This effect, called the Yarkovsky effect for asteroids or Yarkovsky-O'Keefe-Radzievskii-Paddock effect for rotating bodies, has been measured on near-Earth asteroids, but applying it to 3I Atlas requires assuming the comet has very specific thermal and surface properties that seem unlikely for an icy body. As these explanations were debated, new data arrived that made everything more confusing. Ground-based observatories detected a faint emission feature in 3I Atlas's spectrum that hadn't been seen in previous observations. The feature appeared at a wavelength corresponding to ionized oxygen, specifically the forbidden emission line at 630 nanometers. This line is associated with thin, hot gases in low-density environments. Seeing it in a comet's spectrum is unusual but not impossible. Comets can produce ionized gases when solar ultraviolet radiation or the solar wind interacts with their comas. But 3I Atlas's coma is extremely faint. The density of gas surrounding it is too low for significant ionization to occur through standard mechanisms. The detection sparked speculation about alternative energy sources. Perhaps 3I Atlas has an internal heat source that's ionizing gases released from its interior. Radioactive decay in certain isotopes can produce heat over millions of years. If 3I Atlas contains unusual concentrations of radioactive elements, Internal heating could drive outgassing from beneath the surface, potentially explaining both the trajectory change and the ionized emission. But this requires the object to have a composition radically different from any known solar system comet, formed in an environment enriched in radioactive isotopes far beyond normal stellar abundances. Alternatively, perhaps the ionization comes from electrical effects. If 3I Atlas has accumulated significant electric charge during its journey through interstellar space, discharge events could ionize surrounding gases, while also producing forces through electromagnetic interactions with the solar wind. This is highly speculative and lacks supporting evidence, but it's been proposed for other anomalous comet behaviors in the past. The scientific community remains divided. Papers are being prepared with different interpretations. Observing time on major telescopes is being allocated for intensive follow-up studies. Everyone wants more data, but 3I Atlas isn't cooperating. The object is now moving away from both Earth and the Sun, becoming progressively fainter as distance increases. Within a few months, it will fade beyond the detection limits of all but the largest telescopes. The window for detailed study is closing. What makes this trajectory change particularly significant is the context. 3I Atlas has displayed multiple anomalies since its discovery. Its composition shows isotope ratios inconsistent with solar system objects. Its thermal properties don't match standard comet models. Its rotation state suggests recent disturbance. And now it's changing direction in ways that don't fit outgassing models. Individually, each anomaly might be explained by rare but natural conditions. Collectively, they paint a picture of an object that consistently defies expectations. Some researchers have begun questioning whether 3I Atlas might not be a natural comet at all. The possibility that it could be an artificial object, a probe or debris from technology, has been raised cautiously in a few academic settings. The trajectory change, if not caused by natural outgassing, could potentially result from active maneuvering. The ionized emission could be propulsion-related. The thermal and compositional anomalies could reflect manufactured materials rather than natural planetary formation products. These ideas are met with significant skepticism, rightly so. Extraordinary claims require extraordinary evidence, and nothing observed definitively points to artificiality. Everything could still be explained by rare natural processes we simply haven't encountered before. But the fact that such discussions are happening at all indicates how puzzling 3I Atlas has become. Scientists don't casually invoke artificial origins. The default assumption is always natural phenomena unless proven otherwise. For researchers to even consider alternatives suggests they're genuinely struggling to fit observations into conventional frameworks. And the trajectory change has intensified that struggle. There's also a historical parallel. In 2017, when Oumuamua made its close pass through the inner solar system, it exhibited non-gravitational acceleration that couldn't be explained by detected outgassing. The similarity to 3I Atlas is striking. Both are interstellar visitors. Both show acceleration without clear propulsive signatures. Both have unusual shapes or rotation states. Both have sparked debates about artificial origins. The difference is that with Oumuamua, we only had a few weeks of data before it disappeared. With 3I Atlas, we've been watching for months and will continue observing for several more months. We have time to gather the evidence needed to solve the mystery, if we can recognize what we're looking at. The trajectory change also raises questions about predictability. If 3I Atlas can alter its path in unexpected ways, can we accurately predict its future trajectory? Right now, models show the object on a hyperbolic orbit that will take it out of the inner solar system over the next year, eventually returning to interstellar space. But if additional trajectory changes occur, those predictions could be wrong. The object might pass closer to planetary orbits than expected, or it might take longer to leave the solar system. Given that 3I Atlas poses no collision threat to Earth, this is more of academic concern than practical danger, but it highlights how much we still don't understand about interstellar visitor behavior. Researchers are also examining whether the trajectory change correlates with other observable phenomena. Did the object's brightness change at the same time? Did its rotation period alter? Were there any changes in the spectroscopic signatures beyond the ionized oxygen line? Detailed analysis of archival data is underway. If correlations exist, they could provide clues about the underlying mechanism. If the trajectory change happened in isolation, with no other observable effects, that makes it even harder to explain through conventional processes, which typically produce multiple signatures simultaneously. One team is investigating whether the change could result from an impact. If 3I Atlas collided with a small interstellar dust grain or debris fragment at its high velocity, the impact could transfer momentum and alter the trajectory. At 80 kilometers per second, even a grain weighing a few grams would deliver significant energy. But the probability of such an impact during the narrow window when the trajectory changed is extremely low. Interstellar space contains dust, but it's spread very thinly. The odds of a chance collision happening exactly when it was observed are similar to winning a lottery. Possible, but suspiciously coincidental. Another line of investigation involves gravitational influences we might have missed. Could there be an undiscovered body in the outer solar system, a distant planet or large asteroid, whose gravitational field perturbed 3I Atlas? This seems unlikely because such a body would need to be quite massive and relatively nearby to produce the observed effect, and we've surveyed the relevant region of space fairly thoroughly. But the possibility hasn't been completely ruled out. Some researchers are using the trajectory change to place constraints on the possible locations and masses of hypothetical outer solar system objects. If a Planet 9 exists, could it have influenced 3I Atlas? As scientists work through these possibilities, the object continues its journey. Real-time tracking shows it's now approximately 2.1 astronomical units from the Sun, between the orbits of Mars and Jupiter, receding at over 80 kilometers per second. Its apparent brightness has faded to magnitude 19, requiring professional-grade telescopes to detect. Amateur astronomers who followed it earlier can no longer see it. Within another month it will drop below magnitude 20, and only the world's premier observatories will be able to track it. By mid-2025, it will effectively vanish, lost in the depths of space, carrying its secrets with it. The January 9th trajectory change has energized the scientific community in ways few astronomical events do. Comets are usually predictable. They follow their orbits. They outgas when heated. They fade as they recede. 3I Atlas refuses to be predictable. Each new observation seems to deepen the mystery rather than resolve it. And that's both frustrating and exhilarating. Frustrating because we want answers. Exhilarating because we're witnessing something genuinely new. Whatever caused the trajectory change, whether exotic outgassing, unusual surface properties, internal activity, or something we haven't considered, it reveals that interstellar space contains objects with properties and behaviors we didn't anticipate. Our models are built on studying solar system bodies, objects that formed here and evolved under local conditions. When visitors arrive from other stellar environments carrying histories shaped by different formation processes and interstellar exposure, they often surprise us. 3I Atlas is teaching us that the diversity of objects in the galaxy exceeds our solar system sample. The investigation continues. More observations are planned. More data will be analyzed. More papers will be published. And eventually, consensus might emerge about what happened on January 9th. Or perhaps the mystery will persist, another unexplained aspect of an object that consistently defies explanation. Either way, 3I Atlas has secured its place in astronomical history as one of the most puzzling interstellar visitors we've encountered. If this examination of 3I Atlas's impossible trajectory change has captured your imagination, hit that like button and subscribe for ongoing coverage as this story develops. We'll be following every new observation and theory as scientists work to explain what happened. Drop a comment with your thoughts on what could cause a comet to change direction with no visible propulsion. This is the kind of cosmic mystery that reminds us how much we still have to learn about the universe beyond our solar system.